A simple piece of dark metal snaps to your refrigerator door. 6,000 miles away, a multi-ton maglev train glides effortlessly above its track at hundreds of miles per hour without ever touching the ground. These are entirely different machines, yet they run on the exact same invisible force. So, what exactly is this invisible pull? And how did we learn to harness a power that requires no batteries, no wires, and no fuel to pull solid metal across an empty void? Human interaction with magnetism dates back roughly 2,500 years to the ancient Greek region of Magnesia. Here, people stumbled upon a strange mineral that seemed to defy the rules of nature. They called it lodestone, a naturally occurring iron oxide that could effortlessly snap up small iron objects. To early humans, this was literal magic. A stone that could reach out and grab another piece of metal without any physical contact defied every known law of physics at the time. It took centuries before anyone found a practical use for this phenomenon. Around 200 BC, Chinese scholars carved lodestone into a smooth, spoon-shaped device and placed it on a bronze plate, where it would consistently align itself along a north-south axis. They had built the world's first compass. By pointing a reliable path through trackless waters, that simple piece of aligned rock allowed sailors to navigate the open oceans with precision. For generations, humanity used a tool they barely understood. We were observing the effects of magnetism, but to build the modern era, we had to stop observing and start reverse engineering the invisible mechanics inside. The transition to a scientific understanding began in the year 1600. English scientist William Gilbert realized that a compass needle points north because the Earth itself acts as one massive magnet, reclassifying magnetism as a measurable physical property of the planet. To see how it actually works, you have to look at the atomic level. Inside every piece of iron, there are billions of microscopic zones called magnetic domains. You can think of them as tiny, independent magnets. In a standard piece of iron, these domains point in entirely random directions, canceling out each other's pull. But when these chaotic arrows are forced to point the exact same way, their individual forces combine, projecting a unified, massive magnetic field. This atomic teamwork is rare. It only happens in specific ferromagnetic elements, like iron, nickel, and cobalt, because their unique atomic structures are flexible enough to let these domains shift and lock together. Magnetism is the physical manifestation of perfect atomic alignment, a state of deep structural organization that humans eventually learned how to build from scratch. Today, creating a supermagnet requires a brutal engineering challenge, forcing trillions of reluctant atoms into a permanent, uniform direction. Industrial production begins with these raw ingredients. Precise ratios of neodymium, iron, and boron are thrown into an induction furnace and melted down into a glowing liquid alloy at extreme temperatures. This molten metal is rapidly cooled and then crushed down into a microscopically fine powder. At this stage, the powder is entirely powerless. Its atomic domains are scrambled, holding zero magnetic pull. Then comes the alignment. The dead powder is placed into a mold and blasted with a massive external magnetic field. Instantly, every single jagged particle snaps to attention, rigidly locking into a parallel orientation. To ensure they never move again, the mold is subjected to a process called sintering. Extreme heat and pressure weld the particles together into a dense, solid block without melting the material, permanently freezing those domains in place. The resulting neodymium magnet possesses immense strength, but is physically delicate. The metal is highly brittle, prone to shattering like glass upon impact, requiring specialized coats of nickel or zinc to keep it intact. Industrial manufacturing relies on this intense heat and crushing pressure to permanently lock atomic alignment into a solid state. The mechanical understanding of magnetism expanded in the 19th century when scientists, including Michael Faraday, proved that electricity and magnetism were two sides of the same coin. A moving magnet could generate an electric current, and an electric current could generate a magnetic field. This gave birth to the electromagnet. By running an electrical current through a coiled wire, engineers could suddenly conjure a powerful magnetic force out of thin air, and more importantly, turn it off with a switch. This programmable, invisible force is the hidden engine of modern domestic life. It spins your ceiling fans, powers your washing machine, and reads your computer's hard drive. Scale that up, and heavy industry utilizes the exact same principle. A crane operator can activate a massive electromagnet to pick up thousands of pounds of heavy steel beams, transport them across a scrapyard, and drop them perfectly just by cutting the power. In medicine, we push this force to its absolute limit. Superconducting magnets inside MRI machines generate fields thousands of times stronger than the Earth's natural pull, allowing doctors to safely see right through tissue and bone to diagnose diseases without ever making an incision. And in transportation, engineers use opposing magnetic fields to push entire trains off their tracks. By completely eliminating physical friction, these maglev vehicles can achieve ground speeds that were previously impossible. But this density of power requires immense respect. Mishandling these heavily engineered fields can wipe out advanced electronics instantly, and high-strength neodymium poses severe medical risks if accidentally swallowed by children. Humanity started out looking at a strange rock that stubbornly stuck to the iron nails of a shepherd's shoe. We took that rock, pulled apart its quantum mechanics, and weaponized an invisible atomic force to forge the physical backbone of the modern world.